Hello, ladies and gentlemen. Welcome back. We are on chapter 10.2. In planning for this chapter, ladies and gentlemen, I am going to have to break this into two videos, so make sure you watch the next video underneath this one when we're done. Maybe take a break for a while and come back to it. All right, here we go, ladies and gentlemen. So before we get into chapter 10.2, I want to take a few moments and remind you about normality. Okay, this is one of those conditions that you have to check for, and this has always been one of the sticking points that I've experienced with students in the past. Okay, memorize this, folks. Normality. If the problem states that the population is normal, then the sample size does not matter. Simply say, we are told it is normal, okay? Or it is approximately normal because the population is normal. All right. Blue. If the population does not state that the population is normal and the sample size is larger, I think I said 25 earlier, let's stick with the 30. Okay, is larger than 30. But remember, that's going to change. That's one of those things that fluctuates. Right now it's 30, but then when we run into a different situation, it's going to be a different sample size. This is where trying to keep things straight and not getting them confused and mixed up is going to probably be the most challenging. Okay, so you might want to make flashcards for this type of stuff. All right, and the sample size is large and is greater than or equal to 30. We can state, since the sample size is sufficiently large, the presumption of normal is credible. Okay, that's just one way that you can state it. If the population does not state that if the problem does not state that the population is normal and the sample size is small, let's say less than 30, we must check normality by drawing some sort of graph. If there are no outliers or extreme skewness, we can then state the plot does not indicate outliers or skewness. The presumption of normal is credible. Okay, again, that's just one way that you could state that. All right, here we go, folks. So chapter 10.2, we're going to be specifically talking about estimating a population mean. So again, here are our conditions. Okay, simple random sample, normality, independence. Just remember for independence that the population size should be at least 10 times the sample size. Okay, all right. Now, in this chapter, ladies and gentlemen, or in this section, we are not told the standard deviation. Okay, remember, it's not realistic to know the standard deviation. Okay, so when we do not know the standard deviation, ladies and gentlemen, we're going to use the standard error. When the standard deviation of the statistic is estimated from the data, the result is called the standard error of the statistic. The standard error of the sample mean is S over the square root of n. Okay? Now, this is transformed and called a t-distribution. Okay, this is the t-distribution. When we do not know the standard deviation, we substitute the error S divided by the square root of n of x bar for the standard deviation sigma over the square root of n. All right, the distribution of the resulting statistic t is not normal. It is a t-distribution. All right, now we've got something totally new in this section. Unlike the standard distribution, there is a different t-distribution for each sample size. We specify a particular t-distribution by giving it degrees of freedom. Before I forget, folks, you can print this off. It's right above the video if you want to print this. All right. When we perform inference about the mean using a t-distribution, the appropriate degrees of freedom is n minus 1. That means the sample size minus 1. Use table B. Okay, and I'll demonstrate table B here in a minute. So if the sample size is 20, our degrees of freedom will be 19. If our sample size is 45, our degrees of freedom will be 44. If it's 28, our degrees of freedom will be 27. And if it's 500, well, it would be 499. However, I'm going to show you that our table does not go that high. Okay, so for example, ladies and gentlemen, let's say I wanted to do a 95% confidence interval. And, sorry about that. And, I've got the 19 degrees of freedom. So this is table B. Table B is in the back of your book. You can also print this, okay? So if I go to 19 degrees of freedom, that's right here, ladies and gentlemen, 19 degrees of freedom. And if I want 95% confidence, I'm then going to go down here and I'm going to go up and over. And this is what we will use instead of the Z star, okay? We use what it's called T star, okay? It's the T distribution. So that is our critical value, all right? Okay, let's go back now. Let's say I had 27 degrees of freedom and I want the 95%. All right, so I'm gonna go back to my table. Let me clear this. And I'm going to go to 27. 27 is right here, ladies and gentlemen. So I'm going to go over, and then I'm going to come up. And so my critical value there is going to be the 2.052. All right. Now, clear that right away. If we go to 44, ladies and gentlemen, okay, we would notice that the 44 is not on there. So we then go to the next lowest one. We never go up. So 44, because it's going to be conservative here. It's going to be a little bit wider than it needs to be, but that's okay. Okay, in statistics, they like you to be a little bit conservative with your estimations. So that's going to be a little bit wider than it really needs to be, but that's okay. So here our critical value would be 2.021. Now on this other one, ladies and gentlemen, 500, well, you'll notice, ladies and gentlemen, that 500 is not on there, okay? 500 is not on there. So we would actually go to the next lowest one, which is 100. But I want you to notice something here, folks. Look at how little those critical values actually change between a sample size or degrees of freedom of 100 and the infinite. Okay, there isn't all that much difference, 0.984 to 0.96. So as the sample size gets larger, that critical value does not get affected quite as much. Okay. Let's keep going here. So the density curve of the t-distributions are similar in shape to the standard normal curve. They are symmetric about zero, single-peaked, and bell-shaped. The spread of the t-distribution is a bit greater than that of the standard normal distribution. The t-distribution has more area in the tails and less in the center than does the standard normal. Okay, I'll show you a picture on the next page. This is true because substituting the estimate S for the fixed parameter sigma introduces more variation. Okay, so it's going to be a little bit wider. It's a little bit more variable. As the degree of freedom increase, the density curve approaches the normal distribution. As I showed you here, notice again, as our degrees of freedom goes up, as our sample sizes increase, okay, those critical values are not all that far apart, okay? Let's see, this happens because S estimates the population standard deviation more accurately as the sample size increases. So using S in place of the population standard deviation causes little extra variation when the sample is large. All right. So you can see here, ladies and gentlemen, that the bigger dash, the flatter one, okay, let me do this in green. Okay, so this one, degrees of freedom of 2, that's this flatter one right here. Okay, degrees of freedom of 2, that's a pretty small sample size of 3, because remember degrees of freedom is n minus 1. There's more area in the tails. And then as we increased the 9 degrees of freedom, that would be a population size of 10. Okay, that's this one right here, ladies and gentlemen. It's a little more peaked and a little less in the tail. And then the standard normal curve is the solid line. So as the sample size gets larger, that is going to approach what the actual normal curve looks like. Okay? Now, here is what our formula looks like for the t-distribution. All right, right here, x bar plus or minus t star times the standard deviation over the square root of n. Now, t again is that critical value that we find in table B. Again, this is table B. Notice right here, ladies and gentlemen, it says the t-distribution critical values. Okay, and we're going to have to use this table. There's really no way with the calculator that we can do this. So we're going to have to know how to read this table. So you probably will want to print this table. All right, so I'm going to go through some examples, and I'm going to go through some that are completely put together already that I got when I was at a training several years ago. And then I'm going to do one example that you can print out on a printer if you want to. All right, here we go. So these are kind of cool. You ready? All right, the confidence interval for a population mean. Okay, these are kind of funny. They're kind of cool. Okay, I really like these PowerPoints. About those heights, squirrels. Okay, we've got some interesting squirrels and heights, right? Okay, here we go. You're gonna laugh at this. At least I hope you laugh. In the long ago prehistoric ice age past of Minnesota, saber-toothed squirrels roamed the landscape of Minnesota from river to river. Okay, recognize him? Ooh, look at that squirrel. Those squirrels are extinct, but their species have evolved into the modern squirrel. Okay, I'm not even going to try to say that word. And is found in Heights, Minnesota. Their teeth are thought to be slightly smaller these days. Yeah, I hope so. But how small are they? It has been difficult for the University of Minnesota biologists to determine their teeth size. There are various and effectively defend their home. They are vicious, sorry about that. They are vicious and effectively defend their homes and food supplies. Okay, squirrels at home, squirrels on food defense. All right. A U of M biologist professor recently disguised himself as a Heights squirrel and unobtrusively gathered some data on the incisor length of these creatures. Squirrels' long teeth are incisors, unlike the long canines of the biological professor. I wish we were in class doing this. All right. Step 1, remember the inference toolbox, folks. Step 1, identification of the parameters of the procedure. The statistics, the confidence level, the sample distribution, the confidence interval formula. All right. Again, pause if I'm going way too fast. The variability of the squirrel's incisors is unknown. Squirrel's teeth grow at a fast rate, so a large standard deviation is suspected. We will use our sample data to estimate the standard deviation of the population. So, step 1. The biology professor has decided to estimate the population mean incisor length with 95% confidence. The first task, grab the squirrels. Here's our data. Now, remember, ladies and gentlemen, it's been a while. We can then put this data in list number 1. Okay, then we can do the stat, calculate one variable stats, and the calculator is going to spit out that information. Okay, so the calculator put all of that in list 1, stat, calculate, one variable stats. Step 2, assess the credibility of the presumed population shape and thus the credibility of the presumed sample distribution of the sample mean. Well, since the sample size is small, ladies and gentlemen, guess what? We have to draw a picture. Graphically assess the credibility of the presumption of an at least approximately normal distribution of incisors lengths. So we can say for normality, folks, the box plot does not indicate skewness, thus the presumption of a normal population is credible. Step 3, state the procedure and calculate. So we are not going to use this one because we do not know the standard deviation. So we are going to use x bar plus or minus t star times the standard deviation divided by the square root of n. Now, ladies and gentlemen, so let's just make sure we got this. So our sample size, ladies and gentlemen, is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So that's our sample size, right? So our degrees of freedom, ladies and gentlemen, is 15. All right, so let me go back. Now, you'll notice that our T star, ladies and gentlemen, is right here, 2.131. Okay, just to make sure that we see this clearly. 15 degrees of freedom is right here. 95% is right here. We're going to go up. We're going to go over. And there's our T, 2.131. Okay. Then our standard deviation that we got is 0.11756. We're going to divide that by the square root of 16 because our sample size is 16 and the mean is 2.957. So voila, ladies and gentlemen, do the plus and minus and we get that as our interval. Okay, interpret. Okay, the interpretation in context, and here you must be really, really careful. The confidence interval and the confidence level statements. Interpret the confidence interval in the context of the problem and interpret the confidence level. Okay, note the difference. I am 95% confident that the true mean incisor length of height squirrels is between 2.88 and 3.0133 centimeters. The confidence level of 95% indicates that in repeated sampling, intervals constructed in this way will include the true population mean 95% of the time. Okay, so interpreting the confidence interval and interpreting the confidence level. Don't get those mixed up. All right, ladies and gentlemen. So, but wait. Okay, red card. Suppose you want the same confidence in a smaller interval. Say, for example, we want a margin of error of only 0.01 centimeters. Okay, I did this, ladies and gentlemen, in the last video. okay, except I used Z star instead of T star. All right, not a problem. Well, not for those who are members of the algebraic Illuminati, okay, if any of you get what that is. So what we did here, ladies and gentlemen, is we took our margin of error, we used Z star here, okay, and then we ended up with a sample size of 531. Now, we probably could have also, instead, we probably should have used T star. Not quite sure why the professor used Z star there, but you could just do that with the T star, and that would give you an accurate representation. So we would need a sample size of 531 if we wanted a margin of error of 0.01, according to this, using the Z star. All right, so ethical postscript, folks, ethical postscript. This study was IRB approved, okay? No height squirrels were harmed. They have returned to their study of probability, okay, playing cards. All right, so under FDA regulations, an IRB is an appropriately constituted group that have been formally designated to review and monitor biomedical research, in case you were wondering what IRB is. Okay, ethical postscript number 2. On the other hand, the coin a phrase. However, the U of M biology professor, previously known as Lefty, was slightly harmed during data collection by a particular incisor adept Heights squirrel on food defense. Okay, I hope you appreciated that humor, folks. All right, let's go through another one. Okay, here we go. All right, so this is dealing with medicine. Speaking of knee-jerk reactions. Okay, step 0, understand the problem. So here's our problem. Suppose you are walking along and suddenly feel and hear your knee pop. Your knee gives way and swells significantly. Your body might be trying to tell you that you have an anterior cruciate, I can't even say it, ligament, okay, ACL injury. This is not good. You are now in for some surgery and weeks of rehabilitative work, okay? ACL surgery aims at reconstructing the knee, which involves grafting the ligament to the tibia and femur. This is accomplished using little fixation nails or screws. Okay, there you go. A surgical challenge is to keep the tendon from rupturing again. This brings up the question of force needed to detach the fixation nail. To address this question, a study using 15 human cadaver knees was undertaken after performing the surgery. Tension loading was applied parallel to the longitudinal axis of the tunnel. Okay, tensile loading at the velocity of 50 millimeters per minute was applied to the femur. The loading was continued until graft rupture and failure load was recorded. Wow, okay. So here's our data. So those are the pull-out forces. We wish to estimate the mean pull-out force for this type of fixation nail in ACL surgery by constructing a 95% confidence interval. Step 1, identification. Statistic, confidence level, okay, the estimated sampling distribution. State the procedure you are using. Okay, we're using the T procedure. Step 2. Assess the credibility of the sampling distribution. So in this case, ladies and gentlemen, we use the normal probability plot. Okay, graphically assess the credibility of the presumption of at least approximately normal pull force distribution. Very important for small samples. Okay, so this is a normal probability plot. Remember, if it's fairly linear, that means it's fairly normal or approximately normal. The plots do not indicate skewness. The presumption of normal population is credible. Step 3, the mechanics, the math. All right, so we plug in those numbers. We've got our X bar plus or minus. Remember, we used the calculator. Let me go back to the data. Okay, where'd the data go? There it is. Okay, there's our data, ladies and gentlemen. So we put this again in list number 1. Then we did the stat calculate, one variable statistics, and we found X bar and we found S. Okay, so we have to use our calculator to find that, and then we can go and plug in those numbers. Oops, one more, and there are the numbers. And again, 95%. So just to review our T star here, so if we go back and look at our sample, ladies and gentlemen, our sample size is only 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 15. So that means our degrees of freedom is 14. And if I go back to the table, ladies and gentlemen, and I go to 14 and 95%, let me clear this off from the last one. You can see that 14 degrees of freedom, 95% is the 2.145. And voila, ladies and gentlemen, that's what we see when we go back to our mechanics, 2.145. Here's our standard deviation divided by the square root of n. All right, so there's our interval. Okay, interpret, again, be really, really careful. So the first interpretation is our 95% confidence interval. Here we go, and then the level. I am 95% confident that the true mean pull-out force is between 424.9 and 515.1. The confidence level of 95% refers to the fact that in repeated sampling, intervals constructed in this way will include the true population mean 95% of the time. All right, let's go look at, we got a couple more here. Okay, I'm going to go fairly quickly, and I'm not going to back up to talk about the different numbers. Okay. All right, the confidence interval for a population mean, here's another one. Venomous snakes are present. Step 0, understand the problem. It is well known that higher vertebrates, such as mammals and birds, exhibit lateralized behavior, commonly described as handiness. Biologists have suggested that laterality may or may not occur in coiling behavior of snakes. A fearless researcher gathered cottonmouth snakes in his lab and reported on the subsequent observations of their coiling behavior. What is our estimated laterality? Okay, left hand, look at how it's coiled, right hand, and then ambidextrous. Step 1, identification, statistics, confidence level, estimate population distribution, the estimated. Okay, state the procedure we are using. Step 2, assess credibility of the sample distribution. Wow, lots of data here. Wow, looks like we got 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. Looks like we have a sample size of 30, which means a degree of freedom of 29. Okay, here they actually used a dot plot. Okay, and they use a box and whisker. You don't have to use both. I would just use a box and whisker. So graphically assess the credibility of the presumption of an at least approximately normal laterality distribution. Very important, again, for small samples. The plots do not indicate skewness. The presumption of normal population is credible. The mechanics. So we plug in all of our numbers. Again, we used our calculator to find the mean. We found the standard deviation. We used table B to find the 2.045, and the sample size is 30. And here is our interval and our interpretation. All right. I am 95% confident that the true mean laterality is between 0.5076 and 0.5612. The confidence level of 95% refers to the fact that in repeated sampling, intervals constructed in this way will include the true population mean approximately 95% of the time. Okay, now one more thing here. So you can print this one off, folks. Let's go through this example. All right, so you measure the weights of 24 male runners. You do not actually choose a simple random sample, but you are willing to assume that these runners are a random sample from the population of male runners in your town or city. Here are the weights in kilograms. All right, now I've printed some of this and some of it I haven't. So, step one, we want to construct, or this is our direction, sorry about that. Construct and interpret a 90% confidence interval to estimate the mean weight of male runners in your town or city. Follow the inference toolbox. All right, so some of this I have printed. Here we go. Pause if I'm going way too fast. Parameter. The population of interest is the weight of all male runners in the town or city. We want to estimate mu, the mean weight of all male runners with 90% confidence. Okay. Conditions. SRS. It states we are willing to assume the runners are a simple random sample. Okay, it states that up here. We do not actually choose a simple random sample, but we are willing to assume that these runners are a random sample from the population. Okay, so there's our SRS, ladies and gentlemen. Okay, now normality. So this is where we would need to take our calculator. Okay, we would need to go to our stat edit, and we would need to put all of those numbers in list number 1. Okay, I'm not going to actually do that because the video is already over 30 minutes. Then we would go to and turn on our stat plot. Okay, number 1. I highly suggest just using the box and whisker plot all the time. So pick the box and whisker plot, the one that shows outliers. And then when you're done, remember you hit zoom and then you pick number 9. Guess I should have gone the other way. Okay, remember zoom 9 is our zoom stat. And that'll create the box and whisker on your graph, okay? If you need to rewind and watch that again to do it, please do so. All right, so this is what we end up with, ladies and gentlemen. When we're all done, okay, we have a box and whisker. And, okay, now on this box and whisker, I'm just gonna put the numbers. Kind of looks like that. It's pretty normal looking. The minimum is 53.1. This is 58.35. The median is 62.1. Q3 is 65.3 and the maximum is 69.3. And so then we can say the distribution is fairly symmetric, therefore we are given no reason to doubt the normality of the population. Okay, if you wanted to, you could do the normal probability plot, but you know, the box and whisker pretty much works with everything. Independence. We must assume that there are at least 240 males in this town, remember 10 times the sample size, town or city, and that each runner is not repeated in the sample. Okay, calculations. So this is where we're going to go, okay, well, we're going to use X bar plus or minus T star times S over the square root of N. Okay, now we plug the numbers in. So we found that X bar is 61.79. We found S to be 40 or 4.8. Our sample size is 24, and now our T star. Now remember, ladies and gentlemen, it said 90% confidence, and our degrees of freedom is 23. So I'm going to go back to the table. So our degrees of freedom is 23, and 90%. So our T star is 1.714. All right, so now I'm going to go ahead and go 61.79 plus or minus 1.714 times the 4.8 divided by the square root of 24. Okay, and then I have 61.79 plus or minus. Okay, figure out, okay, that over there on the right first, and you should get 1.679. Okay, it's better to round more decimal places than too few, so try to stick with at least 3 to 4. All right, now if I go ahead and do the plus or minus, ladies and gentlemen, I get 60.111 to 63.469. So the interpretation, ladies and gentlemen, we are 90% confident that the true mean weight of males in this town or city is between 60.11 kilograms and 63.469 kilograms. All right, I believe that was it for that. Yep. All right, ladies and gentlemen, I'm going to end this video now. You have to watch the next video because there's going to be some new information in there. Okay, watch it. I'm also probably going to show you some calculator stuff. All right, ladies and gentlemen, we'll see you soon.